Let's get started. So our second speaker is Yadong Wu from the University of Hong Kong, and he will be talking about detecting quantum capacities of continuous variable quantum channels. So Yadong, please take it away.
Thanks, Yuxiang. Thanks for all the organizers of this conference. Here I'm going to talk about how to detect quantum capacities over a continuous variable quantum channel. So this is a joint work with my supervisor, Julie Kiribella, and I'm currently a postdoctor working at Hong Kong University Computer Science Department. I'm going to talk about how to benchmark or test capacity over a quantum communication channel or a quantum memory device. So both these quantum communication channel and the quantum memory device is a very important component in a quantum network. And to assess the performance of these quantum devices, the central figure of merit for these devices is their quantum capacity. It quantifies how many qubits we can transmit or store per use of this device in principle with optimal encoding and decoding. To assess a realistic implementation of this quantum device, we need some protocol to estimate the quantum capacity only from the experimental data. So another motivation here of our paper is we try to find some connection connect the quantum information theory with a real quantum experiment. So in quantum information theory, we have many of these rigorous mathematical information concepts like capacity, entropy. So different quantities may have different operational meaning in various quantum information processing tasks. Then on the other side, we have in a lab, we have some uncharacterized noisy quantum channel. We may have some probe quantum state, and we may perform some feasible quantum measurements. So usually, people who care about quantum information theory and people who care about the experiments are two groups of people. But here, in this paper, I try to propose a protocol which we think can be experimentally implementable to detect certain the one-shot quantum capacity over an uncharacterized noisy quantum channel. So this task may look similar to quantum process tomography because in both cases we want to learn some information from the measurement data about this unknown quantum process. But here, instead of fully reconstructing the quantum process, we only care about how many qubits can be transmitted over this quantum channel. That is, we only care about detecting its quantum capacity. So some difficulties in detecting quantum capacity to explicitly calculate the quantum capacity is very tough in the most general case. So it involves a difficult optimization, and which can be done not. So without the assumption of very simple noise model, we cannot give the explicit calculation expression for the quantum capacity. Then to calculate the quantum capacity also require us to have a classical description of this quantum device. But this requires us to perform quantum process tomography. And as we know, process tomography is a really resource-consuming process. So for the sample complexity can scale exponentially with respect to the number of qubits. And we also want to consider the most general scenario, that is, in each use of this quantum device, the noise can keep fluctuate with respect to time. And also the device can, there can exist correlations between the noises in each use of this, across these multiple uses of the quantum communication device or quantum memory device. And even this quantum communication channel can be under control of an adversary during the communication between Alice and Bob. And in this paper, we will focus on continuous variable quantum information that is encoded in quantized electromagnetic field or quantum harmonic oscillator. And it has an infinite dimensional Hilbert space spanned by this quantum number n from 0 to infinity. And if we measure the position or momentum, the outcome has a continuous spectrum. And the continuous variable system is also an important platform for realization of quantum technologies. Let me try to summarize what I have done in this work. So we proposed 2 protocols to estimate lower bounds on the quantum capacity over a continuous variable quantum channel. And these protocols are fit in the realistic scenario, that is, the number of uses of the channel device is finite. And the first protocol is for the general non-ID noise, that is, the noise can keep changing. There can exist correlation between multiple uses of the device. And the second protocol is for certain particular type of ID noise. For the non-ID noise model, we have this, so we use this, in the figure, we use this big box to represent some certain mode quantum channel, but in what channel it is, we don't know what is inside this box. Then we randomly pick some modes as the input to as our test modes, and the remaining modes are used for the purpose of communication or storage. And the corresponding test output modes, we perform quantum measurements and send this classical outcome to do some information processing to decide whether to pass this test or fail. So if we pass this test, then we will infer a lower bound on the quantum capacity over the remaining modes used for communication with certain high confidence level. Note that this lower bound is just a statistical inference result. It's not a derived lower bound on quantum capacity for some known characterized quantum channel. And the example for this claim about after we passing this test is, we may say the average quantum capacity per mode is certified to be no less than 1.3 with certain high confidence level, 99.9%. Here, this 1.3 is our lower bound on the quantum capacity given in this test protocol, and this confidence level is some parameter we can tune in this protocol. Otherwise, if we fail the test, then we have no conclusion on the what is the quantum capacity over the remaining over the other uses of the device. It means that we simply don't trust this quantum device anymore for communication or storage. Here, since we considered finite uses of the quantum channel, so we, instead of considering the asymptotic quantum capacity, we will consider the one-shot quantum capacity. So for a n-mode quantum channel E, the one-shot quantum capacity with respect to a certain error epsilon is just the maximum number of qubits that can be transmitted over E with optimal encoding and decoding, and with the error in the maximal infidelity smaller than epsilon. Here B is just the dimension of the encoded Hilbert space, and D is the optimal decoding, and phi is the encoded state. F E B denotes the maximal fidelity between the encoded input and the decoded output. In the special case, when this n-mode quantum channel is just copies of the same noisy channel, then the asymptotic quantum we can achieve the asymptotic quantum capacity by making this n goes to infinity and the epsilon goes to 0. So here we consider one-shot quantum capacity because for one-shot quantum capacity we can consider the arbitrary correlated noise between among multiple uses of the channel device, and we can consider finite number of uses of this device, and the decoded information, the fidelity we can have a non-zero error in our decoded information. So due to these reasons, we will try to detect a lower bound on the one-shot quantum capacity over multimode quantum channel. So for suppose this channel is denoted by En, representing n-mode unknown quantum channel, and the input state denoted by sigma. The input system is A prime. A purification of the sigma is capital denoted by capital psi. Then at the output side, the joint state at both the input and the reference modes are denoted by rho. With the output state denoted by B and the reference denoted by A. Previous result has shown that the one-shot quantum capacity can be lower bounded by such an expression. Here, eta is a small parameter between 0 and the square root of epsilon over 2. Then this smooth max entropy over unknown state to n-mode state rho is just the minimum of the max entropy over state rho inside a small neighborhood of around rho. Then to estimate a lower bound of one-shot quantum capacity over E is simply reduced to estimate a bound on this smooth max entropy of unknown state rho. Since this inequality is true for all the input state sigma, we can simply choose some state which is experimentally feasible to easy to prepare. Here we choose this n-mode input state to be copies of single mode thermal states, and the purification of a thermal state is just a two-mode squeezed vacuum state. So one mode of the two-mode squeezed state is fed into the noisy channel, and the other mode is kept as a reference mode. Then given n-mode channel, we randomly select the k modes for the purpose of test. Then the task is to estimate the lower a bound on the smooth max entropy at the 2 times n minus k mode state rho. And this estimation of the smooth max entropy of over this quantum state can be reduced to estimation of max entropy over a classical quantum state obtained by performing quantum measurements at the reference modes. So here, for each reference mode, we randomly select to perform our quantum measurement into one of the two conjugate measurement bases. So we randomly either to measure the moment position or with a half probability to measure the momentum. Then the classical outcome system is denoted by X. The classical quantum state is denoted by omega. By using the entropic uncertainty relation, we can find this inequality to bound this smooth max entropy of quantum state by a smooth max entropy of the classical quantum state plus two constant terms. Here, the parameter Xi and Xi prime should satisfy this equality. And the parameter D denotes the discretization width of our continuous outcome. So remind that the measurement outcome is theoretically is a continuous outcome, but in realistic scenario, we only have finite resolution, so we must have this D larger than 0. That is the discretization width of the this continuous outcome. Then to estimate, the problem is reduced to estimate the bound on this smooth max entropy of this classical quantum state omega. And this can be further bounded by performing some correlation test, that is to perform same quantum measurements at the corresponding output test mode, then compare the correlation between the pair of output mode and the reference mode. If there is a strong correlation between these two outcomes, then the max conditional entropy should of this state omega should be upper bounded by a certain function of the correlation between the two outcomes. And then we can further lower bound the one-shot quantum capacity over the other n-k uses of the quantum channels. And this entanglement-based detection protocol is equivalent to the following measurement prepare and measurement protocol. So in this prepare and measurement protocol, Alice as a sender, she prepares at each test mode. She either prepare a position squeeze the state or squeeze the state at position basis or momentum basis. Then he apply a displacement operation with amount of displacement is sampled over a discretized Gaussian distribution, and at the corresponding output side, Bob perform this projective measurement, obtaining measurement outcome XB. Then they calculate the distance between these two values, XA and XB, average over all the K test modes, then compare it with a certain threshold. If this average distance is less than a certain threshold, then we pass this test, and we can obtain an inferred lower bound on how many qubits that can be transmitted over the other remaining n- uses of the quantum channel with certain small error probability. So here, if we want to increase our inferred lower bound on the quantum capacity, we can reduce the value of this threshold T. But at the same time, by reducing this threshold T, we will make the test harder to pass. So there is a trade-off of this choosing the threshold. And the transmission for the purpose of quantum communication or quantum storage can be achieved by feeding half of a two-mode squeezed state into each use of n-1 channels. Then we are done with the non-IID protocol, and I'm going to talk about the second protocol, that is for the identical and independent noise. So in this case, the mode channel is just copies of a single mode noise channel. And again, we choose our input state to be two-mode squeeze vacuum state. And at the output side, we have n copies of unknown state tau. And then the asymptotic partition property tells us that this max entropy over n copies of tau can be upper bounded by n times the conditional entropy or a conditioned B over the state tau plus certain small term. And plugging this inequality to our first inequality of the one-shot quantum capacity, we obtain the following inequality, and the estimation of lower bound on one-shot quantum capacity is reduced to estimate this conditional entropy. And to estimate this conditional entropy, here we add two more assumptions on the noise. So we first assume this channel is a Gaussian channel, that is to preserve the Gaussianity of the input state. Then the second assumption is this channel is a phase insensitive channel, that is, it always commutes with any unitary any phase rotation unitary operation. And under these two assumptions, the estimation of this conditional entropy can be reduced to estimate only the variance of the cojector at the reference mode and the output mode, together with the covariance between these two cojectors. And again, this entanglement-based protocol is equivalent to a certain prepare and measurement protocol. And here the advantage is that we don't need to prepare squeezed state because we don't use any uncertainty principle. We just prepare coherent state, which is much easier to be implemented. And at the input side, Alice first prepares certain vacuum state and apply a displacement operation with amount of displacement sampled from a flat distribution denoted by X. And at the corresponding output side, Bob performs measurement in the coherent state basis, obtain outcome Y. Then they calculate the cross correlation between X, the values of X and Y, as well as how much amount of noise is added by the channel in by estimating the variance of Y. Then higher cross correlation between these two values of X and Y, together with a lower added noise in Y, will indicate a higher values of quantum capacity. And we also did some numerical simulation on our result, using our theoretical bounds. And this figure shows the bound on the one-shot quantum capacity per channel versus the number of uses of the channel device. So I want to talk about the detail of the numerical simulation, but there are 3 points we learned from this numerical simulation. The first is we find that the lower bound given by the IID protocol, the second protocol, converted much faster to the asymptotic limit compared than the general protocol. So it means the general protocol really consumes much more sample complexity to achieve a non-trivial lower bound on the one-shot quantum capacity. And the second, in the general protocol to detect quantum capacity, if we want to raise the inferred lower bound, we must increase the ratio of the numbers of modes used for testing. Or we can reduce the discretization with D. That's the equivalent. We can say we need to increase the resolution, the accuracy of our measurement device, or we can reduce the threshold. But by reducing the threshold, we may make the test harder to pass. And thirdly, another important parameter I have not mention is the cutoff parameter. That is, if the measurement outcome exceeds from negative alpha to positive alpha, then we just take the value to be either negative alpha or positive alpha. So this cutoff value should be large enough to make sure we get a non-trivial lower bound. Otherwise, as the pink curve shows, when this n goes to large, we may give a trivial lower bound if this alpha is not large enough. Then this is the summary of my talk. So we proposed two protocols to estimate lower bounds on quantum capacity over a continuous variable quantum channel simply only from experimental data. And the first protocol is for the general non-IID scenario, and the second protocol for particular IID noise. And both protocols can be implemented using the current technology on optical platforms. And they can be used to validate practical quantum communication devices or quantum memory device. And in the near future, we may use this protocol to detect useful communication paths in a dynamically changing quantum network. That's all for my talk. Thanks.
Thank you, Yadong, for the very interesting talk. Any question in audience? Any question? So as maybe I was wondering, maybe something into the technical details. I was wondering if you achieve for the proof of non-IID case, whether you achieve that by using some type of, I don't know, quantum definitive theorem for continuous variable channels or states. And if so, can we ask what is the concrete role of, let's say, energy of input here in this task? Because in the continuous variable version, I guess the dimensions should be replaced by something related to energy and also maybe the arrow measure. So may I ask whether there is relation between the energy in the, let's say, the input state you use for tests and the precision of your
yes.
outcome?
So yes, the energy it does affect a lot in the inferred lower bound. So we didn't show the expression for the lower bound, but actually it does affect. And we did some numerical simulation, and it makes sense. Then if we have higher energy in our input state, we can get a higher inferred lower bound. And actually, alpha is another parameter. We make this cutoff. We make this truncation in this measurement outcome. So this alpha must be large enough. Otherwise, we may give a trivial lower bound on the expression of the lower bound may become just equal to 0 if this cutoff is not large enough.
I see. So did you really use some continuous variable definitive theorem, or did you just use maybe the finite dimensional one using cutoff?
No, we didn't use definitive theorem here. So actually, at the beginning of this project, I did thought about using definitive theorem, but after I derive a lower bound using definitive theorem, and then I compared that bound with the bound here in the first protocol, I find that actually this bound scales much better than the bound derived from definitive theorem.
I see. Interesting.
Yeah. Thanks.
Any other question? I guess if not, let's maybe thanks Yadong again, and let's proceed to our next speaker.